All right, it's going. So we're talking about parallel resistors in a circuit. All right, and we'll draw a simple diagram similar to our little demonstration that we just did. So here is the source. Okay. So we'll say we have a positive voltage on this side and a negative voltage on this side. And the first way to think about it is as if this is a parallel plate system, all right? And therefore we have, if you want, an electric pressure, electrostatic pressure, which attempts to push current from the positive plate to the negative plate. So if we put a resistor in the way of that, or in the path of that current that's being pushed that way, okay, and if that happens to be a light bulb, we'll see that that starts to allow current to pass, and the light bulb glows, and we understand that energy is being used as it travels from the high voltage to the low voltage. If we add another resistor in parallel, okay, we notice that both of these bulbs burn equally brightly, which is different than what happens if we put them in series, okay? We took our ammeter and we measured, and we found that with a 120 volt source, and we saw that we had 0.6 amps traveling through this branch. We also had 0.6 amps traveling through this branch, okay, and these were identical bulbs. And if we were to measure right here, we put an ammeter here, we found that it was about 1.2 amps, so double, right? So what we want to talk about is why is it and what's the mathematics of this? So the first thing that must be true is if there's no bulb here, right? If this bulb weren't here, we'd have 1.6 amps traveling around this circuit. We measured that, okay? When we add a new bulb, we get another, current traveling through this branch, and the overall current in the whole system doubles or goes up. So for current to go up, all right, that must mean that resistance has gone down. So if we look at our Ohm's law formula, we kept this constant, 120 volts, all right, and we saw a rise in current. Well, R, resistance, is proportional to the reciprocal of I, or inversely proportional to it. So in other words, resistance must have dropped. Okay, so what's the math on this resistance drop? And I guess before we talk about that, we should talk about why is overall resistance drop as we add resistors in parallel, because this is exactly the opposite thing that happens when they're in series. As we add resistors in series, right, resistance goes up. To me, one of the easiest ways to think about it is to imagine a water balloon filled with water, okay? And if we poke one hole in it, water should be blue. We poke one hole in it somewhere, you get a little stream of water flowing out, right? So if you think about the positive plate here that we sort of talked about before, if we allow one pathway for electricity to go through, even if it's got a high resistance, a little stream will come through, right? If we add another path, well, that's similar to poking another hole, right? Now we have another path. Okay, and as we continue to add more and more holes, right, the overall flow, we added up this entire flow like we were doing here, okay, the overall flow grows. The more holes we add, right, the less resistance to water coming out of the balloon there is. Does that make sense? So you have to be a little bit careful, right? Say you're wiring your home. You can't put, I believe, and don't quote me on this, but I believe it's something like you can have a maximum of 11 maybe lights on one circuit, for instance. So there's rules that you have to follow, because every time you add something in parallel, right, you're going to increase the amount of current traveling through your wires, right? In your home, there's generally fuses on each individual circuit, and if you go down to your fuse panel in the basement, right, each one has its own breaker. And usually, depending on how your house is wired, they can do a maximum of about 15 amps. You guys ever blown a breaker in your house? Doing what usually? What usually causes a breaker to blow in your house? Yeah? So like, I would say I am running the toaster and I fire up the microwave, and for whatever reason I plug in the vacuum at the same time. Often some scenario like that will blow a breaker, right? Each of those things is current heavy. They use a large number of amperes when they're running, and they overcome that 15 amp maximum on the circuit, and the circuit blows, right? We're adding resistors, which decreases the overall resistance. So there's a mathematical formula for sorting out how that works, and we'll do that after I add a new layer. Oops, color. And we'll write it in green now. Okay. So the math of parallel circuits. So we'll do an example circuit here. And I like to start thinking them as parallel plates always. To me, that helps, right? We studied parallel plate systems. We understand there's a push from the positive to the negative plate. Okay, and what we'll start doing is we'll start putting resistors here in parallel. So R2, R3, R4, and so on. Okay, so the total net, right, resistance that this that this voltage will, in a sense, see or experience is found this way. Okay, so you add up the reciprocal of all of the resistors, okay, up to however many there are in parallel, all right, and you divide that number into 1, and that will give you the net resistance of the entire circuit, okay? So I think there's room here to try an example. Just redraw a quick circuit here. And let's see, we have 5 ohms, 6 ohms, 2 ohms, all in a parallel situation. So basically, we just want to know, from the perspective of the source, what is the entire overall net resistance of this circuit. There are other ways that you can write this formula. This is my preferred way. I think it's the easiest to understand what's going on. So 1/5 plus 1/6 plus a half. I'm just going to calculate that. Just give me a second. So I get 1.15 for that. Maybe double check and see if that's what you guys get. Okay, so the R net, this circuit here, is 1.15 ohms. Something to notice is that your net resistance will always be lower than the lowest resistor in here. Okay, and that should make sense, right? If only that resistor existed, okay, that would be the resistance of the circuit. So if none of these were here, the whole circuit would have a resistance of 2. But we said that as we add resistors, we lower the overall resistance. So a quick way of checking is to make sure in your parallel circuit, the net resistance that you get is lower than your lowest resistance. Okay? So maybe we'll put up one problem here and give that a try. See how you guys do. It's a nice color. All right. So try this on your own. I'll do it on here, but I'll try not to talk while I'm doing it. Okay, so this is what I want you to do. Find the total current, total resistance, and I and R, not R, sorry, I and V, so voltage drop, across the following circuit. Put 6 volts on there. Okay? So what you got to do is you got to find the total current leaving the battery and therefore returning to the battery. The total resistance of the entire circuit. Okay? So another way to talk about that is the equivalent resistance. So the equivalent resistance of this entire circuit. And also the current through and the voltage drop across each of these resistors. One thing to note here, before we do this, what is the voltage drop across each of these? Right off the bat. Each one is connected to a parallel plate system with plus 6 volts and 0 volts. So what is the voltage drop here? What do you think? Do you think it's 2? Does anyone disagree? Let's imagine that neither of these resistors is here. What would the voltage drop be across here? 6 volts, right? 6 volts. Let's imagine that none of the other 2 were here. What would the voltage drop be across here? 6, right? If you think about it, that should make sense, right? If you think about this as a parallel plate system to which we've added pathways for electricity, right? The charge that's here, right, is only passing through here, right? So it's got to be passing through then a potential difference equal to what it is here to here, or a delta 6V voltage difference, right? So each of these pathways has amounts of charge that, you know, that carry the same number of, or same amount of energy with them as they travel through here, okay? So if you want to think about it as train cars, the train cars here are fully loaded, right? The train cars that don't go through here continue on. They haven't lost anything yet. And then they turn the corner and come down here. Okay, they haven't lost any energy. They're going to lose it all here, right? So it's 6 volts across each one of these junctions. And maybe we'll just make a note about that so we don't forget, okay? Every resistor in parallel has the same voltage drop. So in this case, we can answer this really quickly. Everybody gets 6 volts. Okay, they all get 6 volts. But what's more interesting is what is the current through each of them? And how are we going to figure that out? Okay? So I'm going to solve this. Don't look at what I'm doing. I'm not going to talk. See if you guys can solve it on your own. Okay? Okay, is that enough time for people? Okay, so just let me grab your attention for a sec. If you're not done, that's fine. Just for the sake of this being a totally slightly less boring video that I'm doing here, that's going to be on. It's going to be awesome. Little nose blow. Okay, so total resistance is the first thing you got to figure out. So here's your equation. You should have got 0.92 ohms for a total resistance for that circuit. Everybody get that? Perfect. Yes. Right? That's for a series circuit. This is for a parallel circuit, right? It has different rules. Okay, so just double check your notes from yesterday to make sure that you get the difference between the two, right? So this is multiple paths to ground. Series circuit would mean that the current would have to travel through all of these. They would just be, around the loop. So if you look, the equivalent resistance of this circuit is 0.92 ohms. Therefore, I equals V over R. We should get about 6.5 amps traveling through this total. And then you use Ohm's law, I equals V over R for each of these. So you have a 6 volt here through a 2 ohm resistor, so you get 3 amps there, 2 amps here, and 1.5 amps through the far one. And if you add all those up, right, 3 plus 2 plus 1.5, that should equal the total current traveling through the system. And that should make sense, right? Whatever leaves here comes through, splits up into each branch, and then travels back into the circuit at the end. Are there any questions about that? Is that pretty straightforward? Okay, perfect. That will end this video. And